Electricity now. Number 1, part A says state Coulomb's law and give its mathematical expression. I'm gonna give you a few seconds to answer the question and then I'm gonna come back and show you the answer. So Coulomb's law states that the force is directly proportional to the product of the quantity of the charges and it's inversely proportional to the distance between the charges squared. Part B is a direct application on the formula in part A. The formula is F is K Q1 Q2 over R squared, where K is the proportionality constant, which is 9 times 10 to the power of 9. I'm gonna give you a minute to answer the question and then I'm gonna come back. So Q1 is minus 3 nanocoulomb, which is minus 3 times 10 to the minus 9 coulomb. Q2 is plus 5 nanocoulomb, which gives you 5 times 10 to the minus 9 coulomb, and the distance between the two charges is 2 centimeter, which is 2 times 10 to the minus 2 meters. Put that in the equation, you'll get 9 times 10 to the 9 multiplied by the absolute value of Q1, which is 3 by 10 to the minus 9. The absolute value of Q2 will give you 5 times 10 to the minus 9 over the distance between them squared, which is 2 times 10 minus 2 squared. All of that will give you 3.375 times 10 to the minus 4. Number 1, part C says define electric field. I'm gonna give you a few seconds to answer the question and then I'm gonna come back. So the electric field is the force F experienced by a test charge Q0 placed in an electric field divided by the quantity of the charge Q0. Number 2, part A says find the magnitude of the electric field at a field 0.4 meters from a point charge Q equals to 2 nanocoulomb. I'm gonna give you a few seconds to answer the question and then I'm gonna come back and show you the answer. So the formula for the magnitude of the electric field is E is equal to K Q over R squared, where K the proportionality constant is 9 times 10 to the power of 9. So that is 9 times 10 to the power of 9 times Q, which is 2 times 10 to the minus 9, so minus, over 4 meters squared, and you will get 1.12 Newton per Coulomb. Number 2, part B says the electric field caused by a certain charge at a distance 2 meters from the charge is 4.5 times 10 to the power of 5 Newton per Coulomb away from the charge. What is the charge? So you need to find Q. You have the distance equals 2 centimeter. You have the electric field. The magnitude is 4.5 times 10 to the power of 5 Newton per Coulomb. And you also have the proportionality constant K. It's 9 times 10 to the 9. So the formula is E is equal to K Q over R squared. Solving for Q, that will give you Q equals E times R squared over K. Substituting, you'll get 4.5 times 10 to the power of 5 multiplied by 2 times 10 to the minus 2 squared all over k, which is 9 times 10 to the power of 9, and that will give you 2 times 10 to the minus 8 coulombs. Number 3, part A says find the distance from a charge of 16 nanocoulomb where the electric field due to that charge has a magnitude of 4 times 10 to the power of 4 Newton per coulomb. I'm going to give you a few seconds to answer the question, and then I'm going to come back and show you the answer. So you have Q, it's equal to 16 nanocoulomb, which is 16 times 10 to the power of minus 9 coulomb. You also have the magnitude of the electric field, it's 4 times 10 to the power of minus 4 Newton per coulomb. You also have K equals 9 times 10 to the power of 9. So the formula is E is equal to K Q over R squared. Solving for R, you will get radical K Q over E. Substituting, you will get 9 times 10 to the power of 9 to 16 times 10 to the minus 9 over 4 times 10 to the power of 4. And the answer will be 6 times 10 to the minus 2 meters. Number 3, part B says a point charge of Q is 6 nanocoulombs is located at the origin. What is the magnitude of the electric field vector at the point coordinates minus 15 cm on the x-axis and minus 20 on the y-axis? I'm gonna give you a few seconds to solve it and then come back. So you have two axes, and you have Q located on the origin, and then you have minus 15 on the x-axis and minus 20 on the y-axis in centimeter. They wanted to find the electric field E, which is K into Q over R squared. R squared is radical 0.15 squared with 0.20 squared because of Pythagorean theorem, and you have to convert the centimeter to meter, and then you have all of it squared also. Then you have K, which is 9 times 10 to the 9. You also have Q, which is 6 times 10 to the minus 9 from nanocoulomb to coulomb. And then you have E is equal to this, which is equal to 8.63 times 10 to the minus 2 newtons per coulomb. Number 4 says 3 charges lie along the x-axis as shown in the diagram. Here on the origin you have Q2, you also have Q1, and here you have Q3. The positive charge Q1, which is 4 microcoulombs, it's at x equals 4, and the positive charge Q2 equals 8 microcoulombs is at the origin. A negative charge of Q3 is placed on the x-axis such that the resultant force is 0. What is the x-coordinate of Q3? I'll give you a few seconds to answer the question, and then I'm gonna come back. So they told you the net force of X is equal to 0, which means that F13 minus F23 is equal to 0. So F13 equals F23, which means that K to Q1 Q3 over R squared is equal to K Q2 Q3 over R squared. You can remove K and Q3, which will give you Q1 Q2 over R squared and over R squared. So now we have Q1 over R squared equals to Q2 over R squared. This is R13 and this is R23. So you have 8 times 10 to the power of minus 6 over X squared is equal to 4 times 10 to the power of minus 6 over 4 minus X squared, and that will give you 2 is equal to X squared over 16 minus 8X plus X squared. After that you'll get 32 minus 16X plus 2X squared equals to X squared. And then now you have delta, which is B squared minus 4AC, and B is the minus 16 minus 4 to 1 into 32, which will give you 128. Then after you do the X equals minus B plus minus radical delta over 2A, you will get X equals 13.66 or 2.34. This is greater than 4, so it's cancelled, and this is the correct answer.
Let's do number 5. Consider 3-point charges located at the corners of a triangle as shown in the diagram, where Q1 equals Q3 equals 3 microcoulombs, Q2 is negative 8 microcoulombs, and A is equal to 0.12 meters. Part A is asking us find the magnitude of the force F1 of Q1 on Q3. So now Q1 is here and Q3 is here. Since they're both positive, will this be an attractive force or a repulsive force? Obviously repulsive, because like charges repel. So since it's on the it has to act on this line, so on this diagonal, so I'm just going to do this because it's by Q1 on Q3. So this is, let me call this F13 or F1. So how do you find the magnitude of the force? You use Coulomb's law. F equals K Q1 Q3 over R squared. R is the distance in meters. Since we know that A and A is 0.12, so obviously the length of this, the hypotenuse, would be A radical 2. So once we substitute, we get 9 times 10 to the power of 9 times Q1 and Q3 are the same, so it's 3 times 10 to the power of minus 6 coulombs, all of it squared because they're the same, and it's A radical 2, so 0.12 radical 2, all of it squared, and you should get as your final answer 2.8 newtons. Let's do part B as well here. Part B is asking us the magnitude of the force F2 of Q2 on Q3. Now look at the charge of Q2. Q2 is negative, Q3 is positive. So obviously it's an attractive force. Let me use the red pen here. So this is F2 on 3, right? So the magnitude of this would again be k q2 q3 over r squared. Now for this question, for any question, the product of the charges always has to be positive because we're looking for the magnitude, right? So again, it's 9 times 10 to the power of 9 times 8 times 10 to the power of minus 6 times 3 times 10 to the power of minus 6. Now over the distance is a this time, so 0.12 squared. And for this you should get the answer of around 15 newtons. So that's your answers for parts A and B. Let's continue with parts C to E. What do they want in part C? What is the X component of the resultant force on Q3? D says what's the Y component, and E is what's the magnitude of the resultant. So I'll give you a few seconds, all of you can solve. I've given you a quick diagram of what the scenario is right now, and we'll check in a few seconds. Okay, let's check together. First question is, what's the X component? But first, let's look at the diagram here. So F1 signifies the force by Q1 on Q3. F2 represents the force by Q2 on Q3. So again, Q1 and Q3 both are positive. That's why F1 is going away from Q3. Q2 and Q3 and Q2 is negative, whereas Q3 is positive. That's why it's an attractive force. That's why it's going towards Q2. So with that in mind, let's define our positives and negatives. So this direction is positive for X and the up direction is positive for Y. Now F2 is fine with the X axis, but F1 we have to resolve it. Now I've given some angle measures. So since it's both A and A are congruent, it's a 90 degree angle. So now since these are congruent, these angles, so this is also 45 degrees. So I know that this is F1 cosine 45, and I know that the vertical one is F1 sine 45, right? So the first question is, what's the X component of resultant force? So obviously the X component would be F1 cosine 45 minus F2. So you would get something like 2 minus 15, giving you minus 13 newtons. Another way to represent this would be minus 13 I newtons, so you would know that it's the X component. Part D now. What's the Y component? There's only one force along the Y axis. That's F1 sine 45. So the Y component is simply F1 sine 45, giving us an angle, a force of around 1.99 newtons, approximately 2 newtons. Again, you can put this as 1.99 J newtons. 1.99 J newtons. Just to be like, it's positive up. Part E is very easy. What they want is the magnitude. So you have to take square root 13 minus 13 squared plus 1.99 squared. So it's 13 squared plus 1.99 squared. And the magnitude of the resultant is approximately 13.2 newtons. And that's your answers from numbers C to E. Let's do number 7 now. An electron of mass 9.11 times 10 to the power of minus 31 kilograms enters the region of a uniform electric field, as shown in the diagram, with initial velocity equals 2 times 10 to the power of 6 meters per second, and the electric field is 300 newtons per coulomb. The width of the plates is 0.25 meters. Part A says find the acceleration of the electron while in the electric field. So now let's think about, first thing that should come to mind when they're asking us for acceleration is forces. What force is causing the acceleration, right? Well, there are two forces acting on it, right? The electric force, because there's an electric field, and the weight. Now, the reason why I haven't drawn the weight here is because look at the mass. Look how small the mass is. This mass is so small that the weight can be considered to be negligible. So we don't need to use it in our equations. Now, if anyone remembers, the equation, the formula for electric force is equal to Q times E, right? Now since we have the electric force pointing upwards, and since the charge of the electron is obviously negative, then the force has to be downwards. The direction has to be affected. So now if anyone remembers Newton's second law, which means sigma F net equals ma, right? So using these two equations, we have to do Fe equals QE and F net equals ma. We have to equate these two because the electric force is the net force, which gives us QE equals ma, right? Now another thing to keep in mind is this is projectile motion, right? Because it's going down like this. It's not going like, straight down like in free fall, straight vertically down, nor is it going horizontally to the right or to the left. It's going as a curve. So we have acceleration ax like this, and we have acceleration ay. Now as we remembered last year, ax in projectile motion is equal to 0. So technically we're looking for ay, right? So let's just put a little ay here. Now substituting, the charge of an electron, q electron, is a constant, and it's minus 1.6 times 10 to the power of minus 19 coulombs. So now if we substitute, we get minus 1.6 times 10 to the power of minus 19 times 300 equals 9.11 times 10 to the power of minus 31 ay. When we substitute and simplify, we should get ay equals minus 5.3 times 10 to the power of 13 meters per second squared. Now something to help us make it easier on ourselves, we can put a little j here, just to help us realize, okay, it is a vertical force, because if we all remember, x-axis, y-axis, I is here and j is here, right? So this just helps us that it's a vertical force. So we can just put a little j there. And this is the acceleration of the electron. Let's continue with number 7. You guys can do parts B to D. I'll stop for a few seconds. You can pause the videos and then we'll check after a few seconds. Okay, let's start. Part B asks us to find the time it takes the electron to travel through the region of the electric field. So as you can figure out from this question, what they're trying to ask is, how long does it take the electron to cover this distance, the one I've drawn an arrow through? In essence, the length L. So L is given to us as 0.250 meters. And we have the initial velocity v0, which is 2 times 10 to the power of 6 meters per second. Now you must be thinking, oh, we have acceleration, you have to do, UARM equations. Well, that's wrong. Remember, this is a projectile motion, so it has movement in the x direction and in the y direction. For part B, we are interested in the x direction of motion because it has to cover a horizontal distance. And as we remember, ax in projectile motion is 0. So when the acceleration is 0, it's URM. And what is the only equation we've learned in URM? Delta x equals Vt. We have the V, we have the delta x. All we need is the time. So it is t equals L over V0, right? Because L is the distance it has to travel, or the displacement. So 0.25 over 2 times 10 to the power of 6, and the time is equal to 1.25 times 10 to the power of minus 7 seconds. So it only takes a very small amount of time for the electron to travel through the region of the electric field. Let's continue with part C. Part C asks us what's the vertical displacement as it passes through the electric field. So now when we're thinking of a delta y, we have to think of UARM because we have an acceleration. AY exists. So we have to think of UARM equations. The only equation where we have delta y is delta y equals half ay t squared plus v0 sine theta t. Now when we launched the object, it was here and we launched it. What was the angle to the horizontal when we launched it? Wasn't it 0? So this all becomes cancelled because as we all know, sine 0 equals 0. So substituting, we get delta y equals half times minus 5.3 times 10 to the minus 13. 10 to the 13, and the time is 1.25 times 10 to the minus 7, or this is squared. So we should get delta y to equal minus 0.412 meters. So that's the displacement, the vertical displacement the electron experiences while in the electric field. Let's do part D. D asks us what's the velocity when it is outside the electric field. So notice here they're not asking for Vx, they're not asking for Vy, they're asking for total V. So how do you find the V? Well, V is the resultant of this and this. So in effect, the equation we use to find V is the square root of Vx squared plus Vy squared. Vx is very easy to get, it's always constant because there's no acceleration in Ax. So Vx is always 2 times 10 to the power of 6. Vy is the harder one. In UARM, what was the equation we used to get the velocity in terms of acceleration and time? Wasn't it V equals at plus v0? Using that equation, we get Vy equals minus 5.3 times 10 to the power of 13 times the time plus 2 times 10 to the power of 6. Because wasn't that the initial velocity? Wait, no. It's V0 sine theta. And since theta is 0, then V0 sine theta is 0 as well. Now Vy equals minus 6.59 times 10 to the power of 6 meters per second. We have Vx and we have Vy. All we have to do is square root this and square root this, and then we should get the final answer. So what we do is 2 times 10 to the power of 6 squared plus minus 6.59 times 10 to the power of 6 squared. We take the square root of all of that, and what we should get at the final answer is 6.89 times 10 to the power of 6 meters per second. So this is the final velocity of the electron. Let's start number 8, part A. In a thunder cloud, there may be an electric charge of plus 30 coulombs near the top and minus 30 coulombs near the bottom. These charges are separated by approximately 3 kilometers. Find the magnitude of the electric force between them. So I've drawn a basic square here representing the cloud. So you have 30 coulombs near the top and negative 30 coulombs at the bottom, and the distance is 3 kilometers. So I'm trying to find the force between them. So obviously when you have 2 charges and you want to find the electric force, you apply Coulomb's law, which says F equals K Q1 Q2 over R squared. Now one thing that you guys should know is that Q1 times Q2 is always absolute value. So if you have a positive times a negative, doesn't matter, the product should always be positive. So the force has to be it has to be positive in short. So K is 9 times 10 to the power of 9. That's a constant, you should know that. Q1 is 30 and Q2 is 30 as well, because the product has to be negative. And since it's in kilometers, you have to make it into meters. So 3 times 10 to the power of 3, all of it squared, and you should get as the final answer 9.00 times 10 to the power of 5 newtons, because they're asking for a force. Let's continue with part B. Part B is asking us what is the magnitude and direction of the electric field that will balance the weight of 3 protons of mass 1.67 times 10 to the power of minus 27 kilograms each. Okay, so I've drawn a little line here. Let's assume we have 3 protons here, proton 1, 2 and 3. I've combined all the weight forces into one weight, which is 3 mg, because their masses are the same, right? So now we have to think, where does the field go? Let's think about the direction first, then we can get the magnitude easily. Well, first we shouldn't find the field. First we have to find the electric force, and from the force we can get the field, right? So now obviously if this is a free body diagram, the force has to be up, right? So let's call this F electric. It has to go up to balance the weight, right? So let's substitute in the equation. We should get the force electric has to equal the force by gravity, or the weight, right? Again, substituting, the force electric has to equal 3 mg. Now what is the force electric? Well, we should know by now the equation of the force is F equals QE, where Q is the charge and E is the electric field. So that's where we get the E from. So that's why I was saying we shouldn't look for E immediately. Let's find the force first, then we can find the field, right? So, well, we don't have one charge, we have 3 charges. So what we have to do is 3QE equals 3 mg. Well, we do the obvious thing and cancel, and we should get that E equals mg over Q. Now, one thing we should always keep in mind is, what do we use for G? In questions where G is not given, always use G equals 9.8 meters per second. And what is Q? Q is the charge of a proton. This is another constant. It is plus 1.6 times 10 to the power of minus 19 coulombs. It's a constant. And the charge of an electron, so let me call this Q proton. Q electron is equal to the same thing, minus 1.6 times 10 to the power of minus 19 coulombs. Substituting in the equation, E equals, the mass is 1.67 times 10 to the minus 27 times 9.8 over 1.6 times 10 to the power of minus 19 coulombs, and we should get the E equals 1.02 times 10 to the power of minus 7 newtons per coulomb. That's the unit for the electric field. Why I chose 3 significant figures? Because in the given, the lowest number of significant figures is 3. We've answered one part, which is the magnitude. What's the direction? Well, given that the force is upwards, right? And since the charge is positive, well then, the electric field is upwards as well. But what if there were 3 electrons? Then the field would be downwards, because since the charge is negative, negative times upwards makes the direction of the field downwards. So the magnitude is this, and the direction is upwards. And one more thing to notice is that no matter how many protons they tell you, 3 protons, 4 protons, a million protons, no need to worry about the numbers because they cancel anyways. So in essence, what you should know is this formula, E equals mg over Q, for this type of question, where they're asking for the electric field that will balance the weight. Let's do number 9 now. A 45 grams insulating sphere carries a charge Q equals minus 40 microcoulombs and is suspended by a silk thread from a fixed point. An external electric field which is uniform and vertical downward is applied. Part A says, the applied electric field has a magnitude of 2 times 10 to the power of 3 Newton per coulomb. What is the tension in the thread? So now let's think about the free body diagram for a second. This here is the electric sphere. I've drawn the weight down and the tension up because it's suspended by the silk thread. Do you think I've drawn all the forces? No, right? Because it says there is an external electric field which is uniform and vertical downward. Now, as we all know, the electric force is equal to the charge times the electric field. Since the charge is negative, so the direction of the electric force is opposite the direction of the field. Since the field is downwards, then the force is upwards. So let me just draw the force like this. This is the electric force. Now what you have to do is find the tension. They've given us the electric field. So simply sigma Fy equals 0, which gives us a tension plus the electric force equals the weight. So tension equals the weight minus the electric force, which is 0.045 times 9.8, because we always use 9.8 in questions where they don't give gravity equals 10, minus Q times E, again 0.045 times 0.045 times 9.8 minus the charge, which is minus 40 times 10 to the power of minus 6. Now, since we are dealing with the force electric, so we're not looking at the direction here, we're using the magnitude, we cancel the minus. So we just erase it, we remove it. So in this question, The only reason the minus was given to us was to make sure that we know the direction of the force electric, which is opposite the direction of the electric field. So when you're substituting, you substitute it as a positive number, times 2 times 10 to the power of 3, and when you're done solving, the tension should equal 0.361 newtons. Okay, let's continue with part B. Part B says the applied electric field holds the sphere in place above the point of suspension, and the tension in the thread is now 0.45 newtons. Find the magnitude of the electric field. So now a few things have changed. Now let's imagine this as the point of suspension. If the ball before was hanging like this, now it's hanging like this. It's held above the fixed point of suspension. So isn't the tension down now? So this way, now we know that the tension is downwards as well. Well, since two forces are down and we only have three forces, one of the forces has to be up, right? So the electric force is still up. Now let's use again sigma Fy equals 0. This time we are looking for the electric field. So that means we don't know the electric force. So Fe equals T plus W. So we have the T, which is 0.45. We have the weight 0.045 times 9.8. And we should get the electric force equal to 0.891 newtons. Is this the answer? It's not. We're looking for the electric field. Now the electric field, if force E, the electric force, is equal to the electric field times the charge, then isn't the electric field equal to the force over the charge? It is, right? So 0.891, let me just draw a line here, over the charge is 40 times 10 to the power of minus 6. You may be wondering why I'm not using minus 40. The minus just shows us the direction. Since they're asking us for the magnitude, the signs are all positive. And once we solve, we should get 2.23 times 10 to the power of 4. And since the unit of the electric field is Newton per Coulomb, then you have to put Newton per Coulomb. And that's the magnitude of the electric field. Let's do number 1 for electricity, chapter 22. Number 1 has 4 parts. I'll give you guys a few seconds to solve the question and then we'll check together. Let's do part A. State Gauss's law in words and give its mathematical expression. I won't say I won't write the words, I'll just say them and then I'll give the expression. So Gauss's law basically says the total electric flux of a closed surface is equal to the charge enclosed in that surface divided by epsilon 0, which is the permittivity of free space. So I'll just write the formula. This means phi E is the symbol for electric flux, is equal to Q enclosed. You can use a capital Q, doesn't make a difference, over epsilon 0. Part B. When excess charge is placed on a solid conductor, where does it reside? It resides on the surface. C. Write the 3 forms of the general definition of the electric flux. So other than this, the one that I've underlined, there are 3 other equivalent equations. So let's just write that. Phi E is equal to the integration of the electric field vector times the area vector, which is equal to the electric field times dA times cosine the angle between them, which equals the perpendicular electric field times the area, and D. D says, just memorize these 3 equations. You don't need to know the derivation, just memorize. So I'm just boxing this, so you just have to derive this. D says, give the expression of the magnitude of the electric field outside a charged conducting sphere. Since it's a charged conducting sphere, we can use Gauss's law, and then when we derive, we should get E equals, because we want the electric field, not the flux now, 1 over 4 pi epsilon 0 times Q over R squared. This should look familiar because we should know this equals k. So isn't this kq over r squared? Both work fine. Usually k won't be given, so you will have to use this equation. So both are acceptable answers. Let's move to number 2 now. I'll give you guys another few seconds. It's again of many definitions, so you can solve and then we'll check together. Okay, let's check together. What Gaussian surface is used to find the electric field outside an infinitely long charged wire? If we remember, we had derived in class the formula for this infinite charged wire. We had to create a shape for it. What shape did we use? We used a coaxial cylinder, or as in the homework they had mentioned, cylinder coaxial to the wire, which had a radius, arbitrary radius, that means the radius that we choose, r, and height h. B. What is the magnitude of the field of an infinite sheet of charge? It was E equals sigma over 2 epsilon 0. C says field between oppositely charged parallel conducting plates. E equals sigma over epsilon 0. Now I'll just erase the top part so we can have some space. So let me just erase, because I want to solve it on the same page. Now D. The shaded conductor shown in the figure carries a total charge of Q equals plus 7 nanocoulombs. The charge within the cavity insulated from the conductor is Q equals minus 2 nanocoulombs. What is the charge on the inner surface of the conductor? Okay, let's do it together. Now, first we have to assume what is the scenario when there is no inner charge Q. Let's just assume this wasn't there in the beginning. We put it now. We put it later on. So let me just cancel this. So we get rid of this. Since this big Q, right, it's a shaded conductor, this carries 7 nanocoulombs. And inside there won't be anything, because if we remember, inside a conductor, all the charge resides on the surface of it. When you put a minus 2, initially this was 0, this inner part. If we put a minus 2, we're putting minus 2 nanocoulombs worth of electrons inside. Now one thing to remember, can we move protons? No, only electrons can move. When you're putting electrons in the middle, so let me just remove this. Now we have put a minus 2q. When you put electrons, won't the electrons here that I'm going to highlight in red, in this area, won't they be repelled and they'll go on the outside? They will, right? So when electrons are moving, won't the protons be left behind? So any charge that we put in the middle will induce an opposite but equal magnitude charge. So basically you will have plus 2 nanocoulombs in the inner surface, the red surface, or the black as I'm covered it up now. Why? Because when I put minus 2 worth of electrons, the same number of electrons will be repelled, leaving plus 2 nanocoulombs worth of protons left here. So we'll have a positive charge. And that's numbers 1 and 2 done. Let's move on to number 3. We have 4 enclosed surfaces S1 through S4 together with charges Q1 till Q5 are sketched in the figure. We have the values for Q1 till Q5. A to D are telling us to find the electric flux through each of the surfaces. So I'll give you guys a few seconds. I have displayed the formula for the electric flux here as a hint, and we'll check in a few seconds. Okay, let's check. So first they're telling us to find the electric flux for S1. Let me represent it like this. That's the Q enclosed. So Q of S1, whatever exists in that, over epsilon 0. There are no numbers in this question. We keep them in symbols. Now let's take a closer look at S1. I'm highlighting it in red. What is there in S1? Only Q1, right? Yeah. So Q1 is minus 4Q. So it's just minus 4Q over epsilon 0. That's it. B. Phi S2, I'm not going to put the formula again, it's just the same thing, but this time I'm going to do it in green now. What is an S2? Well, it's Q1, Q2, Q3 and Q5. So now coming here, it's Q1 plus Q2 plus Q3 plus Q5 all over epsilon 0, which gives me, what's Q1 minus 4Q plus Q, Q3 is minus 2Q, Q5 is minus Q, all of this over epsilon 0. When we simplify, we should get minus 6Q over epsilon 0. Coming to part C now, let's go back to the thing. It's going to be phi of S3 is equal to, now let's use, I don't know, blue for S3. What is there in S3? All of this. Q4, Q3, Q4 and Q5 are there. So Q3 plus Q4 plus Q5, all of that over epsilon 0, and when you simplify you should get again minus 6Q over epsilon 0, which shows us that the fluxes through S2 and S3 are equivalent. Now part D, this must be S4 obviously. Let's see the diagram, and I'm going to use purple. This is S4, only Q5. Okay, Q5 is minus Q, so let's go here. It's very simple, minus Q over epsilon 0. So all I have to do to find the answers for these kind of question is find the total sum of the charges enclosed in the thing over epsilon 0. And if you have numbers, you substitute. Number 4, part A. A point charge Q 7 microcoulombs is located at the center of a cube of side L of 0.150 meters. 6 other point charges are in there, each having a charge Q equals minus 1.5 microcoulombs, are positioned symmetrically about Q in the cube. What is the electric flux through one face of the cube? And they've given us this permittivity of free space, which is nothing but epsilon 0. I've given a quick diagram. We have the cube with 6 faces, 1, 2, 3, 4, the front one is 5 and the bottom one is 6, and then I've drawn the red dots to symbolize Q. And you guys can solve the question. I'll give you a few seconds. Okay, let's solve. Now we should first of all, before finding the electric flux through one face of the cube, we should find the electric flux in the whole cube, right? But to find the electric flux of cube, shouldn't we find the Q enclosed of the cube? Right? This is our question mark. Epsilon 0 is always a constant. Well, to find that, let's call this, big Q is already taken, Q enclosed. Isn't it 7 plus 6, because 6 faces, times minus 1.5, which gives us minus 2 microcoulombs? That is the Q enclosed. Now, to find the electric flux of the cube of one face, how many faces do we have in a cube? Isn't it 6? So shouldn't it be 1/6 the initial flux? Yes, right? Now since we have minus 2, so it's minus 2 times 10 to the minus 6. Always use the correct units, SI units. 8.85 times 10 to the power of minus 12. And we should get, let's see, minus 3.77 times 10 to the 4. Now what's the unit of flux? It's very long, Newton meter squared per coulomb. And you guys can check. I'll give you guys a few seconds. Okay, let's continue with the next one, part B now. Let's read part B. The total electric flux through a closed surface in the shape of a cylinder is this. What is the net charge in the cylinder? Very easy question. We have the flux, we have epsilon 0, we need to find Q. Well, this is very easy. Since the flux is Q over epsilon 0, cross multiply, shouldn't Q equal flux times epsilon 0, which is simplified to 4.80 times 10 to the 4 into, let's see, 8.85 times 10 to the minus 12, which is 4.25 times 10 to the minus 7 coulombs. One trick to be aware of here is they might ask you how many nanocoulombs this is. Well, for that, that's 4.25 times 10 to the 2 nanocoulombs. They might ask you that, so just to keep in mind. Because as you all know, 1 coulomb is equal, or wait, no. Yeah, 1 coulomb is 10 to the 9 nanocoulombs. So then you can just simplify from that. Let's do number 5 as well. A thin conducting wire, square plate, 35 centimeters on a side, lies in the xy plane. A total charge of 1.96 times 10 to the minus 8 coulombs is placed on the plate. We have epsilon 0. A says find the charge density on the plate, and B says magnitude of the electric field just above the plate. One question that some of you may be having is, we only learned the formula for the infinite uniform plate, right? But since this is a plate only 35 centimeters to a side, this is not infinite. But when they say just above the plate, we are so close to the plate that when you consider the size, it seems infinite. That's the trick here. So now we'll do part A. I'll give you guys a few seconds. Okay, let's solve it together. The symbol for charge density is sigma. That's the total charge over the area. The total charge is 1.96 times 10 to the minus 8 over the area. 35 times 35, but in centimeters, which is going to be centimeters squared. To make it into meters squared, you have to multiply by minus 10 to the minus 4, which gives us 1.60 times 10 to the minus 7. Let me just fix that. Coulombs per meter squared. Part B, electric field. You should memorize the formula. It's sigma over 2 epsilon 0. So this over 2 epsilon 0, I'm not going to write the number. And you should get 9.04 times 10 to the power of 3 newtons per coulomb. Significant figures is very important. Since we have 3 both sides, we should always put 3. That's questions 3 to 5 done. Let's move on to question 6. A conducting spherical shell of radius 13 centimeters, which I've drawn here, carries a net charge of 5.07 microcoulombs uniformly distributed on the surface. A says find the magnitude of the electric field outside the shell, just outside the shell. B says inside the shell, and C says very far away from the shell, what is the magnitude. I've given you some formulas here to give a hint, and you guys can solve for a few seconds before I check with you. Let's check together. First, they want it just outside the shell. As you all know, if it's a conducting, any conducting substance, it will have all the net charge on its surface. So when they're asking just outside the shell, we have a charge, so we have an electric field. Now, since we know that phi equals E dot dA, the integration of all that, which equals Q over epsilon 0, since we know it's a net charge which is uniformly distributed, we know that the field will be constant because everywhere is the same thing. It's very uniformly distributed. Like this, like this, like this, like this, like this, right? So we can take the integration out. So E times, what's the area of a sphere? 4 pi r squared equals 5.07 times 10 to the minus 6 over 8.85 times 10 to the minus 12. We can substitute r, make sure it's in meters. We should get that E equals 2.70 times 10 to the power of 6 Newton per coulomb. And I want you guys to note on one special property here, that we can also use the equation E equals kq over r squared. Even though this is a very old equation, this also works here because it's a conducting spherical shell. Part B now. What's the magnitude of the electric field inside the shell? Since we know all the net charge is on the outside of the shell, is there anything inside? No. Very easy. E is 0. C. What is the magnitude of the electric field at the point very far from the shell? Since we know this equation that I'm underlining here, what they're asking us is when r tends to infinity, what does E equal? Oh wait, sorry. What does E equal? Well, if r is infinity, then r squared is infinity. Anything over infinity, isn't it 0? So E equals 0. So this is why this equation helps us for this part C. Let's move on to question 7 now. A conducting spherical shell again, having an inner radius of 5 centimeters and outer of 6, carries a net charge of 9 microcoulombs. If a plus 4 microcoulomb point charge is placed at the center of the shell, determine the surface charge density or sigma. Part A says inner surface, B says outer surface. So what I want you guys to remark on is, this is just a shell and the solid part of the shell is only the part I'm highlighting in black. Anything inside is hollow. You can think of, it's basically like a ring, a big metal ring, right? So the inner radius is 5, the outer radius is 6, so the thickness is 1. Let me use red. 1 centimeter. So I'll give you guys a few seconds. You can solve. I've given you some hints. The outer surface is 9 microcoulombs and we have just put a 4 microcoulomb charge inside. And then we'll check together. Let's check together now. Now for the first one, they're saying the inner surface. Since we know that this part is the outer surface, this is the inner surface. Since we have put a 4 microcoulomb charge inside, this induces a -4 on this part. Now I have explained before, I'll explain briefly again. Basically I put a 4 microcoulomb charge. Electrons are attracted to this area, they're attracted to positive. So -4 microcoulomb charge will be induced here. So this is equal to Q over A, right? Charge over area, which is -4 times 10 to the -6. Now we are talking about a sphere, right? So it's 4 pi. Radius is 5 centimeters, so 0.05 squared, which should give us -1.27 times 10 to the -4 coulombs per meter squared. Part B now. Let's call this sigma 1. Now we are looking for sigma 2. Outer surface. Now let me just erase everything actually, so that it becomes simple. Let's just make, okay, that's big, like that, and let's just quickly make another one smaller. Never mind. Yeah, this is good enough. Perfect. I had a -4 here last time and I had a +4 here. Putting the -4 here, what do you think this causes? Well, it causes a +4 here on the top part of the inner part, right? The top part of the inner surface, and that +4 again causes a -4 on the bottom part of the outer surface. Seems complicated. If you think about it, it's not. Since we know that the net charge has to be 9 microcoulombs, well, the sum of this and x has to be 9. X minus 4 equals 9, x is 13. So we have a 13 microcoulomb charge on the outside, so that our net charge is 9. So again, using this, Q over A, 13 times 10 to the -6. Now again a sphere, so now the radius is 6 centimeters. And this time you get a positive answer, 2.87 times 10 to the power of -4 coulomb per meter squared. Okay, let's continue, and this is the answer. You can check for a few seconds and we're moving on to number 8. Let's move on. Number 8. We have two infinite non-conducting sheets of charge which are parallel to each other in the figure. Both sheets, let's do parts A to C because they all have the same given. Sigma 1 and sigma 2 are positive. So I've split the question into two parts, so it's easy. I'll give you guys one hint that, you know what, I won't give you hints. We'll solve it together. Okay, let's check the answers. Now, we should know that the formula for a single uniform plate of charge, which is infinite, is equal to sigma over 2 epsilon 0. That's one thing we should be knowing. So let's just do it. At point A, what is the electric field? Now, if you think about the field as like a force, let's think of it as a force for now. Sigma 1 is positive. When it's positive, the field points away. So at A, it will point away. Let's call this E1, E caused by 1. And for sigma 2, it's positive as well, so it will point away, left and right. So this is E2. So isn't E at A equal to E1 plus E2, which is sigma 1 over 2 epsilon 0 plus sigma 2 over 2 epsilon 0. And now since sigma 1 equals sigma 2, they're the same, so it's sigma, which I've replaced by 1 over 2 plus 1 over 2 is 1, so over epsilon 0, which gives us 6.00 times 10 to the power of 7 newtons per coulomb. They've asked us, we don't need to say, but let's just say it's left. Extra details, it helps. So that's part A. The electric field points to the left at point A. Let's move on to part B. Now it's the same given, part B. And now we're just looking at point B. Now since sigma 1 is positive, it points away, so to the right. So this is E1. And now since sigma 2 is positive, it points away, E2. Since these two are the same magnitudes, they cancel out, 0. C. Again at point C, both are positive, both point away. Now it's again the exact same calculation, so it's everything here, copy paste, equals 6.00 times 10 to the 7 Newton per coulomb. Only one change. What is that change? It's pointing to the right. These questions are very easy. You just have to read the question very carefully. DEF, sigma 1 is positive and sigma 2 is negative, but they have the same magnitude. Let's look at part D. Now in part D, we know that we're looking at point A, sorry. Since sigma 1 is positive, it points away yet again. But since sigma 2 is negative, when it's a point is negative, the electric field points towards it. So it's like this, it points towards it. Since they both cancel out, 0. E and F. I'm going to skip E now, let's move on to F. Same logic for point C. Since sigma 1 is positive, it will point away. Sigma 2 is negative, it points towards 0. They both cancel out. Let me just erase this. And now we'll solve part E. Now, since sigma 1 is positive, points away, and since it's negative, sigma 2, it points towards it, so like this. So using that same logic, E at point B is equal to sigma 1 over 2 epsilon 0 plus sigma 2 over 2 epsilon 0. One thing to be careful of, in the calculations, we don't consider positive negative, it's always positive, okay? We're looking at magnitudes here, not direction. We're just looking at magnitudes here. That's sigma over epsilon 0, giving us the exact same answer as before, 6.00 times 10 to the power of 7 newtons per coulomb. Which direction? Pointing to the right. Look at number 9 now. A non-uniform electric field is directed along the x-axis at all points in space. The magnitude of the field varies with x, but not with respect to y and z. Axis of cylindrical surface 1 meter long and 0.5 meters in diameter is aligned parallel to the x-axis. Two electric fields E1 and E2 at the ends of the cylindrical surface have these two magnitudes and are directed as shown in the diagram. Find the electric flux entering the cylindrical surface at the left end. B says leaving at the right end. C is the net electric flux and D is net charge enclosed. So I'll give you guys a few seconds. I've given a hint here and we'll check in a few seconds. Okay, let's check. Now what are these dA lines I've drawn here, these vectors? Well, the dA is the vector that is, it's the area vector and it's perpendicular to the area itself. Since the area of the circle is here, it's perpendicular, pointing outwards. Same goes for this. As we all know, a cylinder is two circles and a rectangle, which is bent, and I have a dA pointing upwards. I will not need this dA because if there is no E perpendicular to it or close by, I have no use for this dA. Now, many of you will notice that E1 and dA have opposite directions. That should mean that flux is negative, right? But since they're asking entering at the left end, we do not need to care about the signs yet. So sigma flux, the flux, electric flux from the left is equal to E dot, E dot dA vector. Since we know that the magnitude is 5 times 10 to the 3 and the area is pi r squared. Now what's r? R is 0.25 since the diameter is 0.5. And we should get 982 Newton meter squared per coulomb. B now, same thing to the right. Exact same formula. Now this time the flux, the electric field is different, it's weaker. By the exact same radius, the cylinder is not getting smaller and we should get 295 Newton meter squared per coulomb. So for parts A and B, we haven't really cared about the signs. For C, we will need to care. We want the net electric flux. Since I'll just erase this to help us. Since they have defined x, y and z like this and x is shown to the right, they are assuming the right side to be positive. Since my flux is is to the right here, it's positive, but this flux is here because one is negative. So E net is equal to the flux to the right minus the flux that we got to the left, which is 295 minus 982, which is minus 687 Newton meter squared per coulomb, and that's the net flux. Last part D, they want the net charge. Very simple. This E, I'm just going to consider the net, is Q enclosed over epsilon 0, which means Q or Q enclosed is the flux times epsilon 0, which is minus 687 times 8.85 times 10 to the minus 12, and finally we get minus 6.08 times 10 to the minus 9 coulombs, and that's the net charge enclosed in the cylinder. Last question for chapter 22 is number 10. We have 3 hollow concentric spherical conductors. They are charged as follows. The inner one has minus 2q, middle one has plus 3q, outer sphere carries minus q. I'll give you guys a few seconds and you can solve. Okay, we should remember that the charge of any conducting sphere is usually at the outside. On the surface, so we have minus 2q here. I made the thing small so it's visible. Since we have minus 2q here, we cause a plus 2q to come here. I have explained this before. Now since the whole middle sphere contains plus 3q, this should have plus q. And this answers our first part of the question, which is asking what is the charge on the outer surface of the middle sphere. It is plus q. The sum has to be equal to the given. Now I'll erase that and we'll continue on. Let's make it small again and red. We have plus q on the outside. That causes a minus q here on the inner surface of the outer sphere. And since the whole outer sphere has to contain a minus q, outside is 0. So now going back, B says find the charge on the outer surface of the outer sphere. 0, because the inner surface has all the charge. And that's it. Very simple. Hey guys, lesson question number 1 of chapter 23. You guys can do parts A to C and then we'll check them together. Okay, let's solve part A. What is the electric potential energy of 2-point charges Q and Q0 at a distance r apart? It's just the formula. U is the electric potential energy, and since we have 2-point charges Q and Q0, it's K Q Q0 over R. That's it. B, a pair of charged metal plates. So let's draw it like this. Top is negative and bottom is positive. So we should know that the electric field is like this. And we have a positive charge Q. Since Q is positive, the electric field is anyways equal to EQ or QE, and it has to follow the same direction, so it's upwards. So far no calculations, all theoretical. Now part C is where we have calculations. The potential at a certain distance from a point charge is 720 volts and the electric field is 180 newtons per coulomb. What is the charge? So what we know is V is equal to 720 volts, E is equal to 180 newtons per coulomb. I would like to quickly go over the formulas for this. So V is equal to KQ over R, and we should remember that E is equal to KQ over R squared. Do we notice a similarity? We should notice that E can be written as KQ over R times 1 over R, right? Well, doesn't this lead to, let me just continue on the next page. Since we have that KQ over R times 1 over R, this is equal to V. So don't we get E equals VR? So isn't, oh wait, no, sorry. Isn't it E equals V over R? So when we cross multiply, we should get ER equals V, which means R equals V over E, which means it's 720 over 180, which is 4 meters, because radius has to be distance has to be in meters, like this. Now we're looking for the charge. We can use any formula. I personally prefer the V because it's less work. KQ over R, since it's 4, so 720 times 4 equals 9 times 10 to the 9 Q. If we simplify, we should get Q equals 3.2 times 10 to the power of minus 7 coulombs. Let's do number 2 now. We have again 3 parts in number 2. I'll give you guys a few seconds and we'll solve them together. Okay, let's check it together. Part A is asking us, the potential difference between two oppositely charged parallel metal plates is 120 volts and the distance between them is 3 centimeters. Find the magnitude of the electric field between the plates. We should know that basically the formula to find if the field is uniform, V equals ED. That is the main formula we should know. V equals ED, where D is the distance between the parallel metal plates. Because the only time we have a uniform electric field is 2 parallel plates, right? So we're looking for the electric field. So that's E equals V over D. So 120 over 0.03 meters, because we want it in meters. That's 4,000. Now we have many possible units, but a good unit would be, since this is volts and this is meters, volts per meter. Part B now. The potential difference between two oppositely charged parallel metal plates is 450 volts. Find the work done on a charge of 40 millicoulombs as it moves from the higher potential plate to the lower. Now, since naturally, let's say this is the positive, this is the negative. The positive is at the higher potential. The electric field is naturally going from up to down. So there's no external work being done, so the work is conserved. So in this case, the work done by the electric field is equal to the charge VA minus VB, where VA is the high potential and this is the lower potential, which means 40 times 10 to the minus 3 into 450, which is equal to 18 joules. And now part C, when a charge of 20 microcoulombs is moved between 2 points m and n, in a uniform electric field, 240 microjoules of work is done. What is the potential difference between m and n? So now we have the work, we have the Q, but we don't have the delta V, right? Because VA minus VB is delta V. So it's very simple, delta V equals work over charge. Now we don't need to convert into 240 times 10 to the minus 6 because the micro cancels. So it's basically 240 over 20, 12 volts is the potential difference. Okay guys, let's move on to question 3 now. I'll give you guys a few seconds, you guys can solve it and then we'll check it together. Okay, let's check it together. Part A is asking, a positive charge of 4 microcoulombs is moved through an electric field to a point where the potential is 250 volts higher than before. Find the increase in potential energy of the system. Now, you can find some formulas relating potential energy to electric potential, but one you should know is W equals QV. We had used it last time, delta V, sorry. And what we should know is W is equal to delta U. This is also a formula. So if we substitute, we should get delta U equals Q delta V. And this is perfect. We want to find the increase in potential energy. So using this formula, delta U equals 4 times 10 to the minus 6 into 250, because that's the change in electric potential, which gives us 1.0 times 10 to the minus 3 joules. Now part B. But before part B, we have a given. A proton of a certain mass is released from rest in a uniform electric field of magnitude this, directed along the positive x-axis. The proton undergoes the displacement of 0.6 meters in the direction of E. B is asking us, what is the change in electric potential? One thing you should know, the change could be positive or negative. Either it's going from low potential to high potential or high to low. But how do you know which one is it? Well, naturally things tend to go from positive to negative, right? The electric field is like this. And since it's going from rest and having a displacement without any external forces, because they don't mention any, it's from plus to minus. So the change in electric potential, shouldn't it be negative? Because let's say if it's 100 here and it's 50 here, the change is negative. So that's why delta V has to equal minus ED. If you remember, we said V equals ED, so delta V equals minus ED. So it's minus 7.5 times 10 to the 4 into, what's the distance, 0.6, giving us minus 4.5 times 10 to the power of 4 volts. Part C now. Find the change in potential energy of the proton. Again, delta U equals Q delta V. The proton has, now the proton's charge has to be memorized. This is a constant and you guys should know it. It's 1.6 times 10 to the minus 19 times, you get this answer. And then you should get minus 7.2 times 10 to the power of minus 15 joules. And now let's move on to the last part, D. Let's see what they want us to find. What is the speed of the proton after it has moved 0.6 meters starting from rest? One thing I would like you guys to know, since there are no external forces acting, there is one thing that is conserved, mechanical energy. Now, if you remember, we used to say U1 plus K1 equals U2 plus K2, right? But here we're not talking about gravitational potential energy, we're talking about electric potential energy. So what is the energy we have lost? 7.2. But since we don't need to have it negative, it's 7.2 times 10 to the power of minus 15 is equal to half mv squared, right? The kinetic energy, the mass is 1.67 times 10 to the minus 27, yeah. And this is v squared, and the v should be v equals 2.94 times 10 to the 6 meters per second. And this is the velocity of the proton. Let's move on to question 4 now. A 3 microcoulomb point charge is located at the origin, and a second point charge of minus 6 microcoulombs is located on the y-axis at the position 0 and 2 meters. A says find the total electric potential due to these charges at point P. whose coordinates are 1.5 and 0 meters. So I'll give you guys a few seconds. You guys can solve parts A and B and then we'll check. Okay, let's solve it together. First, what we should do is we should find the, let's call the one at origin Q1 and let's call the one at the this position Q2. So let's find V1 first, which is KQ1 over R1, and since it's let's see 1.5 meters away from the axis, so it's from the origin, sorry, 3 times 10 to the power of minus 6 over 1.5, 18,000 volts. Let's circle it because it's not the final answer. Now let's find V2 as well. This is again KQ2 over R2, which is K 9 times 10 to the 9. Now this is minus 6. The sign is important here. Minus 6 over. Now what's the distance? We should do Pythagorean theorem here. Let's see. 1.5 squared plus 2 squared. I'm going to let you guys do all the calculating there, and we should get minus 21,600 volts. And this is circled as well because we still haven't found our final answer. We've just found the electric potential of one and the other. Now let's find the final electric potential. Let's call this V net, and this is equal to 18,000 minus 21,600, which gives us minus 3,600 volts. Let's go part B now. What is the work required to bring a minus 3 microcoulomb point charge from infinity to the point P? Now we should remember what's the formula of what is the question? Work required or potential energy. It is K Q1 Q2 over R. One thing we should know, if R is infinity, isn't U 0? So U infinity is 0. This is one thing. Now if you guys think about it, when you're trying to take something from a lower potential energy to a higher, since we know at point P it's definitely going to be higher than 0, then do you need to do work, or is the work external or internal? External, right? Let's say you're taking a bucket of water. It's not going to go up like if you have a river, it's not going to go up a mountain by itself. It needs to be pushed up the mountain. It's going to fall by itself, but it's not going to go up by itself. So work external here is equal to Q. Now here we have VB minus VA, right? Since we're talking about potentials here, so we have to do Q, which is minus 3 times 10 to the minus 6 into minus 3,600, which gives us an answer of 0.0108 joules. So it's going to take a very small amount of energy to bring it from infinity to point B. Let's move on to question 5 now. I'll give you guys a few seconds and you can check. You can solve and then we'll check together. Let's solve it together. What is the change in potential energy a 16 microcoulomb charge experiences when it is moved between 2 points for which the potential difference is 75 volts? Okay, we should remember that delta U, which is the change in potential energy, is Q delta V. If you know this is very easy, 16 times 10 to the minus 6 into 75, which gives us 1.2 times 10 to the minus 3 joules. That's it. B now. The gap between the electrodes in a spark plug is 0.08 centimeters. To produce an electric spark in a gasoline air mixture, an electric field of 4.5 times 10 to the 6 volts per meter must be achieved. When starting the car, what is the minimum voltage that must be applied by the ignition current? This question is very big, but it's actually very simple. You have two electrodes. One is negatively charged, one is positively charged. The direction of the field is this and it's uniform. Now what is the formula when it's uniform? V equals ED, and we have ED. It's 4.5 times 10 to the 6 into 0.08 times 10 to the minus 2 dividing by 100, and we should get 3600 volts. So this is the minimum voltage that must be applied by the ignition current. And we're done with question 5. Finally guys, let's move on to question 6. What is the speed of a proton of mass 1.67 times 10 to the minus 27 kilograms that is accelerated from rest through a potential difference of 105 volts? So I'll let you solve for a few seconds and we'll check together. Now we should remember conservation of mechanical energy, and we should know the formula for delta U, right? Equals Q delta V. Now now you guys may be thinking, oh, what's Q? Well, for a proton, it's 1.6 times 10 to the power of minus 19. We have delta V 105, which leads to 1.68 times 10 to the power of minus 17 joules. And this is the loss, or it could be the loss or the gain of potential energy. But we're looking for the speed. So we should write delta U equals delta KE. So the kinetic energy loss or gain is equal to the potential energy loss or gain. So then what follows is delta U equals half mv squared. Since it's accelerated from rest, so minus half mv0 squared, v0 is 0, so it cancels out. So now that we have this, it should be 1.6 times 10 to the 68, times 10 to the minus 17 equals half. The mass is 1.67 times 10 to the minus 27. Since the mass is so small, we should expect a very big speed. And the velocity finally is 1.42 times 10 to the power of 5 meters per second. So this is the speed of the proton that is accelerated from rest through a potential difference. Moving on to question 7 now. An electron of mass 9.11 times 10 to the minus 31 kilograms. And one thing to note here, you might need to memorize this. Sometimes they might not give it. So just memorize the mass of an electron. Moving parallel to the x-axis has an initial speed 3 times 10 to the power of 6 meters per second at the origin O. Its speed is reduced to 2.1 times 10 to the 5 at point A. Find the potential difference of VAO of point A relative to origin O. I'll give you guys a few seconds, you can solve. Here I'm just giving a graphical representation of the given 2.1 times 10 to the power of 5, right? And we want potential difference VAO. Now again, conservation of mechanical energy. So we have a certain mechanical energy, let's call this ME1 and ME2. These two are equal, so we can say very easily U0 plus K0 equals UA plus Ka, right? Anything cancelling? No, nothing is the same, so we should continue on. Q times V0 plus half mV0 squared equals Q into VA plus half mVA squared. We have the mass, we have the velocity, we have Q, we have M, V0. All we need to find is VA and V0, right? So when we solve, it's basically the charge of a proton is, electron is minus 1.6 times 10 to the minus 19, V0 plus half the mass. You substitute V0 equals the same charge, you substitute VA, and then you just substitute. I don't have the space here, so I'll just write, you should get VAO to get minus 25.5 volts. So it's going from a higher to a lower potential, right? Moving on, number 8. 3 charges in the figure are at the vertices of an isosceles triangle. Immediately we should know that A, B and AC are equal, and they have said that AB equals AC equals 5 centimeters both sides, and BC is 4. Q1 is plus 4 microcoulombs, Q2 and Q3 both are negative 4. O is the midpoint, so this is 2, 2. A. What is the potential at O due to Q1? So I'm just going to call at O V1 because then it's easy for us. We should know that it's KQ1 over R1. We have K, we have Q1, but we don't have R1, the distance from A to O. How do we find it? Oh, sorry, let me just try to make a straighter line. This is 2. Let's draw a line, black or red actually. Perfect. Well, Pythagorean theorem, so it's 9 times 10 to the 9 times 4 times 10 to the minus 6 over the square root 5 squared minus 2 squared, and when we solve all that we should get 7.86 times 10 to the power of minus 5 volts. B. What is the potential at O due to Q2? Okay, Q2. How do you find that? Using the same formula, KQ2 over R2. We have K, 9 times 10 to the 9. This time we have to use the negative, so it's minus 4 times 10 to the minus 6 over. Now what's the distance? It's obvious that it is 2, right? So it is 0.02, and one thing I forgot to mention here, it has to be in meters, so you have to convert accordingly, and you should get minus 1.80 times 10 to the power of 6 volts. Can anyone tell me something special? V2, or the electric potential at O due to Q2, is equal to V3. Why? Because same distance, K is constant and the charges are the same. So this will be very important when we come to part C. Part C now. Total electric potential at O. So what we have to do is we have to do V1 plus V2 plus V3, and using this we can find our answer. So let's call this V total equals V1 plus V2 plus V3, which is simply V1 plus 2V2, which is, let's write this like this, 7.8 times 10 to the 7.86 times 10 to the 5 plus 2 times minus 1.8 times 10 to the 6, and we should get minus 2.81 times 10 to the power of 6 volts. Moving on to the last part now. A point charge with Q0 with 3 microcoulombs. So now we're finally putting a charge here, and this is Q0. Is placed at O. Find the electric potential energy at associated with QO. U, we're looking for U, is equal to QV. We have the V, minus 2.81 times 10 to the 6. We have Q, it is 3 microcoulombs times 10 to the minus 6. Since the same cancels, it's minus 2.81 times 3. We should get minus 8.43 joules. Not that big of an energy amount, but it's minus 8.43 joules. Finally, moving on to the last question for the electricity required material for the periodic, question 9A. 2 point charges Q1 7 nanocoulombs and Q2 minus 2 nanocoulombs are separated by 36 centimeters. What is the potential energy of the pair? And find the electric potential at a point midway between the charges. I'll give you guys a few seconds and then we'll solve together. Let's solve it together. They're looking for the potential energy of the pair. The very first equation we learned about electric potential is U equals K, Q1, Q2 over R, R being the distance. One thing that is different, you may remember another equation, Coulomb's law, Q1, Q2 over R squared. Here, Q1 and Q2 is not absolute value, negative sign matters, and we will, consider it. So it's 9 times 10 to the 9 times 7 times 10 to the power of minus 9 times minus 2 times 10 to the power of minus 9 over, is 36 centimeters, so 0.36, this cancels, and we should get minus 3.50 for 3 significant figures times 10 to the minus 7 joules. One important thing, guys, we should take care of the significant figures in the exam because marks will be taken for the answers because it's computer correctable. Moving on to part B, last part. Find the electric potential, or the V basically, at a point midway between the two charges. I've called this point M because it's the midpoint. It is 18 centimeters from both sides. We should know that. Let's call VOM the electric potential due to the origin charge on M. So it's K Q1 over R1, which is 9 times 10 to the 9 times 7 times 10 to the power minus 9 over 0.18. Cancels, we should get 350 volts. Now let's call this VAM, which is KQ2 over R2, the voltage electric potential at M due to A. M due to A is equal to 9 times 10 to the 9 times minus 2 times 10 to the minus 9 over again 0.18. Cancels, and we should get a negative 100 volts. Finally, concluding V total equals VOM plus VAM, which is 350 minus 100 to give 250 volts. And this is the end of the electricity portion of the physics periodic. I hope you guys understood, and thank you for watching our video.
Chapter 24, Capacitance and Dielectrics. So what's the capacitance of a parallel plate capacitor? There are two formulas for this, or a couple. There's C equals Q over V. And this just means that capacitance stands for how much charge is needed to produce 1 voltage of potential difference between the two plates. So that's one formula. Then the other formula is this. So 1 farad is equal to 1 coulomb per volt. And then here you have a formula to calculate capacitance, and this is what you end up with, where the higher the area, the more the capacitance, because as you see, you have this parallel plate capacitor. If you have greater area, you can support more charge. So you get more charge per voltage across here. And then the greater the distance, the lower the capacitance, because the more distance you have, the less voltage it will be. So for the same capacitance, there will be less voltage. So that's why the capacitance just changes, or why it's inversely proportional. And then these are the only two factors for constant temperature. So these are the only two factors. The rest are just constants. So epsilon naught is 8.85 times 10 power minus 12. That's a constant. And then that's for vacuum only. If you have another dielectric, like rubber or maybe another insulator, you need to have K. Give the expression, that's what we did. Capacitor acquires a charge, 156.24 volts. Use the formula C equals Q over V. So 156 micro over 24. So this is micro is 10 power minus 6. You apply it here, and that's what you get. Plates of a parallel capacitor in vacuum, 3.5 meters, 4 meters squared, 8.85 farads per meter. So obviously, it's the other formula. It's this formula. 12 times 4 meters squared over 3.54, but millimeters, so times 10 power minus 3. Equivalent capacitance. For capacitance in series, they act like parallel resistors. So it will be 1 over C1 plus 1 over C2 plus 1 over C3 is equal to 1 over C total. So in calculator, what you can easily do is just do 2 inverse plus 4 inverse plus 9 inverse, and then put parentheses, then just inverse that, and you'll get that, instead of trying to write the formula. And then since all of them are micro, you don't have to worry about putting 10 power minus 6, you just put 10 power minus 6 at the end, and you get the answer. Find the equivalent capacitance. This is all parallel, so that's why it's the opposite of resistors, so like you can just add them up. So 2 plus 4 plus 9, which is 15. So 15 micro, so times 10 power minus 6, then we put scientific notation, so this becomes 10 power minus 5. 0.25, again, this is a couple of formulas for energy. So half CV squared. This one you can know, you just have to know one of them. Then you just keep on using C equals Q over V, and then you can substitute here. So this becomes half Q over V times V squared. So V goes, so half QV, or you can do half CV squared, and V is C equals Q over V. So V is Q over C, so equals to half C times Q squared over C squared, and C goes away, and C goes away here, so half Q squared over C. So just memorize one of them, or you can understand the derivation from the internet. It's just integral of Q squared of Q, you get Q squared over 2, like here, and then C is 1 over C is the constant that you take out. So apply the formula, half CV squared, 0.25 times 10 power minus 6 is C, V is 400, and you get the answer. Again here, another formula for energy, like I showed you the derivation. 25, that's the C, you put that in the denominator, and then half of that, 12.5 microcoulombs, straight up forward. Potential difference, 60 volts, 3.5 times 10 power minus 6, again another formula, half QV, V is 60, Q is 3.5 times 10 power minus 6. Okay, a parallel plate capacitor has dimensions separated by 1.4. Bulk light is insulator, the relative permeability 4.9, and dielectric strength is. Dielectric strength is sort of a measure of the voltage that the stronger the dielectric strength, the more voltage you need per meter. So it just makes it less conductible, or more charge is sustainable through the capacitor. So find the capacitance of the device. Again, you use epsilon node, and then since it's resistor K times area over length. Now the area, they gave you this, so just change the centimeter to meter, you multiply, so it's a square or rectangle, so you multiply those two to get the area in meter squared. 1.4 times 10 power minus 3, and K is 4.9 and 8.85. You substitute it in and you get that. What's the maximum energy? You're given this dielectric strength. If you look at the units, you can see it's volt per meter, so if you multiply it by meter, then you'll get the voltage. So to get the voltage, it's 2.4 times 10 power 7 times meter, so the distance between, so 1.4 times 10 power minus 3, and once you get that, you have voltage. Now half CV squared, use the formula, you substitute everything in, and you should get the answer. When a potential difference 175, okay, so charge density is just Q over A. So now you can use the formulas, the two formulas for capacitance, which is Q over V is equal to epsilon node A over D. So now they want spacing, they want D, so D is equal to epsilon node times voltage over area Q. Now Q over A is charge density, and since it's flipped, you have charge density in the denominator. So D is equal to epsilon node voltage over sigma, or whatever the symbol is. You substitute all the variables in and you get it. Small object, it's suspended because of electric field. It gets pushed, so it's not just hanging, it gets pushed to the side because of the electric field. So if we were to draw the free body diagram, you have the weight, and you have the tension making angle like this, or it doesn't matter like this, as long as you support it with either side. So if you did it like that, then positive side is here, negative side is here. Because if you want to know why, 20 nanocoulombs, so it's positive, so it heads towards the negative direction, so the rope makes the angle with the positive, or it's like it's heading towards the positive from the point. So calculate tension in thread. You draw the FBD like I said, showed you there. There's also another force, which is the electric force. I forgot to put that in. mg and here. So to get the tension in thread, you can just get the y component. So Ty is equal to mg. So m is 0.3, g is 9.8 or 10. Then this is Ty. So to get t, this is t cosine 18, because it makes it with a vertical, as you can see there. So 0.3 times over cosine 18, you get t, like here. Now, what's the magnitude of the electric field? Now that you have t, you can use the horizontal component and get t sine 18 is equal to Fe. But they didn't ask for force, they asked for electric field. So electric field is force per charge. So that will be T sine 18 over 20 nanocoulombs. And you just, nano is 10 power minus 9. T, you got it from before, sine 18 is a number. And then you get that answer. Find the potential difference. It's easy. You have electric field. So the units for electric field are either newtons per coulomb or volts per meter. So you use this, you multiply by the distance, which is 0.05. So V times E times 0.05 is equal to V. The E is what you got in part C. Basic 7. Find equivalent capacitance of C1 and C2. Capacitance, it's opposite of resistors, the calculation method. Series, so you do the formula above. So 4 inverse plus 6 inverse, whole thing inverse. You should get like 3.2 times 10 power minus, oh never mind, 2.4 times 10 power minus 6. 3.2 is from another question. C equivalent of C3, which is this one, and C4, which is the equivalent of this. So parallel, you just add them up together. So C3 is 3.6, so 2.4 plus 3.6. You get 6 times 10 power minus 6. What's the potential difference across C1? Parallel means voltage is the same across both branches. So here they have the same voltage, here they have the same voltage. So what's the potential difference across C1? So voltage is 15 across the whole thing. So what is the same between these two capacitors? It's the charge, because charge heads in a straight line. So if it were to be here, then the same amount will be here. Otherwise they wouldn't flow. So Q equals Q, and then you know that C equals Q over V. So CV equals Q. So C1 V1 equals to C2 V2. And you know that the equivalent is 15. So you know the C is 4 10 times minus 6. You don't need to include that. And then here you can just have it X. And then C2 is 6. And then V2, what you can do is 15 minus X. Now you just have one variable, you just solve it, and you'll get the answer. So solve it, you get 9. Find the charge on C3. You know its voltage is 15, it goes parallel. So charge is Q over V equals C. C is 3.6 times 10 power minus 6. So 3.6 times 10 power minus 6 times 15, you get the answer. Number 8. Two capacitors are connected in series with a voltage source, supply line. What's the equivalent capacitance? So series, it's opposite of resistors. So 1 over C1 plus 1 over C2 equals 1 over C total. So a way to do this is 4 inverse plus 16 inverse minus 1. Then you get 3.2 times 10 power minus 6. 10 power minus 6 you can apply to the end, because it's constant, micro. find the charge on each capacitor. You're given the total equivalent and you're given total voltage. And since they're in series, the charge is the same on both of them. So you do C equals Q over V, you need Q, so CV. So C times V, 3.2 times 10 power minus 6 you got, and 50 was the voltage. Then you get 1.6 times 10 power minus 4 charge on each. Now they're disconnected, and then they're connected again, but with parallel. Now they're connected in parallel instead of series. So now, they're not connected in parallel, they're connected in line, so if you assumed it to be like that and like that, it's parallel. So now, you know that they're connected like that, so charge is conserved. So on each of them, it was 1.6 times 10 power minus 4. But since there's two of them, the total is 2 times that, so like 3.2 times 10 power minus 4. That's the new total charge. That's the total charge. Now voltage, the final voltage across each, you need to find that. So this total charge, 3.2 times 10 power minus 4, is equal to Q1 plus Q2, which is equal to C1 V. Since it's parallel, it has the same voltage, plus C2 V. And C1 and C2, you get it from the given above, and voltage is the same, so it's a constant. It's not a constant, it's a variable that you have to find. So this will be 3.2 times 10 power minus 4 divided by C1 plus C2. 3.2 times 10 power minus 4 divided by 4 times 10 power minus 6 plus 16 times 10 power minus 6. That's the final voltage, and then you get 16 volts. Now find the final charges on C1 and C2 respectively. Again, C equals Q over V, so Q is CV. So for the first one, CV is equal to 4 times 10 power minus 6 times 16. And for the second one, is equal to 16 times 10 power minus 6 times 16. And you get the charges. BG9. The square plates of a capacitor measure the area separated by dielectric, voltage rating 400 volts. What's the maximum energy? So there are three formulas for, it's the same formula really, they just substitute C equals Q over V where necessary. So half CV squared. You have C and you have V, so you just substitute it in, and be careful of units. And you get 6 times 10 power minus 4 joules. Find the dielectric constant. The constant is the K of the insulator that makes the permittivity higher. So it's K, the capacitance is K epsilon node area over distance. Capacitance 7.5 times 10 power minus 9. K 8.85 times 10 power minus 12. Epsilon node is that. Area is 0.05 squared. And the thickness is 0.25. Put it in your calculator and you get 84.7 or 84 point something, which is trailing, and then you round it up to 3 significant figures. Next, calculate dielectric strength. Dielectric strength is what it is in the capacitance itself. It's how much it causes the electric field to be, like how the electric field will be because of this insulator. So you know that it's actually measured in volt per meter, the measurement. So this is just a simple way to know the formula. It's voltage divided by distance. So it's voltage 400 divided by distance. So 400 plus 4000 over 0.25 times 10 power minus 3. And you get the answer to be 1.6 times 10 power 6 volt per meter. And that's it for chapter 24.